Alright, what is up my homies, and welcome to Brainmelt University. Today we're going to be talking about the bane of every network technician's existence nowadays, and that is software-defined networking. Not only is it a pain for people who are studying for certification exams, but it's also a pain because software-defined networking is handled a little bit differently by every vendor, which means that no matter what your company uses, you're having to learn a slightly different way of how this works. This video, we're going to focus more on the general side of software-defined networking. We'll also spend a little bit of time focusing on Cisco because they're the largest market share in software-defined networking right now, and they also have the most published material on software-defined networking as their company does it. So we'll go ahead and jump right in. As usual, if you like this video, please feel free to like, subscribe, hit the notification bell, and share with your friends who might be studying for their own IT certifications, because the more engagement we get on this video, the more I will be blessed by the YouTube algorithm god. First and foremost, it's important to remember that there is a difference between software-defined networking and network function virtualization, NFV. NFV and SDN are usually referred to in the same vein. They're usually included in the same chapters when textbooks refer to them. They're usually referenced in many of the same online materials, but they are referring to two very different functions or terms when it comes to networking. NFV, in a nutshell, is simply taking a network device, such as a router, a switch, a firewall, whatever, and moving that to a virtual environment. This is a cost-saving method used by companies that already have some sort of virtualization technology in place, such as Microsoft Hyper-V or VMware vSphere. NFV is simply taking a virtual machine, which is just a piece of a server that's been provisioned to act as its own entity, and installing an operating system normally designed for an intermediary network device. Most virtualization hosts already by default include a virtual switch, which connects all of the individual guest machines from that host together. But you can also actually manually configure a VM to serve as a switch. You just need a lot of port density on that particular server, which might make it pretty difficult. More often than not, network function virtualization is usually used to simulate routers or firewalls, as these require fewer physical interfaces and can usually be handled much better by a virtual instance on a host server. Right now, the entire globe is in the middle of a major chipset shortage, which makes it very difficult when you're trying to order new equipment, and some back orders are almost a year out when it comes to ordering new shipments of equipment. Some companies might not be able to wait that long, especially in the event that a network device fails and that organization doesn't have a spare waiting in storage somewhere. NFV can be a low-cost temporary solution to allow an organization to route all of their information through a virtual router on a server rather than having to go with some cheap off-the-shelf solution that they got at Walmart. For more permanent solutions, this is also a cost-saving method because it's usually cheaper to purchase the license to rent a virtual instance of a device, such as a Juniper virtual SRX firewall appliance or a VM500 Palo Alto firewall, than it is to actually purchase a full-fledged firewall appliance from either of these vendors, mostly because this is supposed to be a cost-saving method. Software-defined networking often is portrayed as cost-saving, but it is extremely expensive, and so SDN is a very different concept. So what's the difference between SDN and NFV? In order to talk about software-defined networking, we first have to talk about the three planes of networking. The three planes of networking are basically domains of influence when it comes to different types of traffic and different types of tasks that are being performed on your network. The three planes of networking from top down are the management plane, which is sometimes referred to as the application plane, the control plane, and the data plane, which is sometimes referred to as the forwarding plane. The management plane is typically referring to how we control our equipment, which is kind of counterintuitive when you're saying this is different from the control plane. The thing about the management plane is this is where all of the information and all of the instructions that a human normally provides to an individual device. If we're thinking about what belongs in the management plane, this can be the telnet and SSH traffic we're using to connect to our devices, or HTTP HTTP for devices that use web interfaces. This can also be the configuration files that we are manually editing on each individual device throughout our network. The control plane, on the other hand, is basically just taking all of this information that's been received from the management plane, and it's using it to build its understanding of the world. It's using this to create all of the different tables and data sets that it needs to be able to do its network function. So all the ARP tables, MAC address tables, routing tables, all of these are created by the control plane using the information provided by the management plane. And finally, we get to the forwarding plane, which is that device actually moving information and making decisions based off of what is contained within its control plane data sources. So now that you have that basic underlying understanding, software-defined networking is simply taking the management plane out of the equation for each individual device. Instead of having to manually connect to each individual device in a particular network segment, an SDN controller can connect and make all of these instruction sets on behalf of a network engineer. This way, you only need to connect to a single device. A lot of times you'll see this referred to as single pane of glass management, and this is where most vendors will draw the line. If you look at things like Ubiquiti Unify, TP-Link Omada, even some Cisco implementations such as APIC EM are all really just central pane of glass management appliances. However, not all vendors draw the line here. Some vendors will actually take control of the control plane as well and directly provide that forwarding information to each individual device. Some of the benefits of this are usually passed off as cost savings by lower cost devices, as your equipment can get away with being dumber and dumber. Less amounts of user interface needs to be provided, which means lower costs for developing the operating systems. You don't need as much CPU capacity or RAM or all of the stuff you normally need to control a device normally just gets pushed to an SDN controller. You're basically creating a network of dumb devices. A lot of these devices do have to be able to operate without the aid of an SDN controller, so they are still a full-fledged device that does have a user interface that you can configure everything that you would want to. It might not just be the most simple or user-friendly. Another major advantage of software-defined networking is it just makes managing your life way simpler. Instead of having to memorize the login credentials for 50 different devices, you log into a single user interface for your controller, and then you push instructions to your devices through that controller. This also increases the utility of your network. You can do things by managing your device through a single pane of glass you normally wouldn't be able to do very easily. You can more quickly make adjustments or changes to your network, or more quickly optimize it, or quality of service adjustments. Whatever you need to do to make your network run more smoothly is usually much easier to do through a software-defined networking implementation. And this also allows for ultra segmentation. One of the biggest problems when it comes to networking security is worms. If a worm manages to make it into a network segment, that entire network segment gets attacked by the same worm. Worms are self-propagating malware that will propagate themselves throughout a specific network segment. If one of your devices in your Seattle office are compromised, you could end up with your entire Seattle office hit with ransomware. So the idea of ultra segmentation is that each individual device will occupy its own /30 subnet. If you're not familiar with subnetting, I'll go ahead and post one of my earliest videos on the subject down below. However, software-defined networking isn't just a pile of roses. There are many disadvantages that come with it as well. The first is that this is extremely difficult to integrate. I mean, you're completely changing the way that your entire network is going to operate and be managed and be controlled. Therefore, it's not just going to be as simple as plugging in a device, flipping a switch, and going to town. It's going to take a lot of time to get this integrated. This is true with both greenfield and brownfield implementations. In a nutshell, a brownfield implementation is where you're trying to integrate SDN into an already existing network. A greenfield implementation is where you're building a network from the ground up as software-defined networking. Usually these are built in tandem with an already existing non-software-defined network, and you slowly phase out the segments of your old network as you implement new segments into your new one. Implementing a greenfield is usually less intrusive than a brownfield, but it's also going to increase the costs in a lot of cases because you have to have two parallel networks operating side by side. You also have to make sure that your network devices actually support SDN. You need to make sure when you buy it that it has the SDN controller listed somewhere in the marketing, because otherwise odds are it's not going to actually take it. A great example of this is Cisco, where a lot of Cisco's older devices, older meaning anything before 2014, could support their old implementation of software-defined networking, which really was just a single pane of glass management solution. However, when they developed their new form of software-defined networking controller, ACI, they required a new piece of hardware to be implemented in their devices called an ASIC. An ASIC is an application-specific integrated circuit, which is basically just a chipset that does a specific task over and over again. Older devices manufactured before 2014 didn't have an ASIC, and so they cannot be implemented into a new software-defined networking solution. You say, well, that was 8 years ago. Well, guess what? A lot of organizations don't upgrade their hardware that often. This also created an issue where devices of the same model group made before a certain period would not have an ASIC, but that exact same model manufactured just a few years later would actually have an ASIC. So you can end up with a situation where, depending on when you purchased it and when it was manufactured, some of your devices might actually integrate into a new SDN architecture, where some of those other ones, which are an identical model, won't. So this is extremely problematic and just something you'll want to be attentive to when it comes to implementing software-defined networks. And lastly, the cost. If your switches in your architecture don't have ASICs or don't support that particular SDN controller, you get to upgrade your switch infrastructure alongside implementing a new SDN controller, which can be extremely expensive, multiple hundreds of thousands of dollars. In addition, there are some tasks that an SDN controller might do that might require additional appliances to be implemented into your network, which means additional costs that you weren't counting on when you first decided to implement. So now let's talk about our different types of SDN controllers. As far as the Cisco CCNA exam is concerned, there's 3 main ones you need to focus on. There is the open standard, which is called OpenSDN. This is actually kind of the first SDN controller that was created, or at least the first useful one. And because this was open source, a lot of manufacturers and vendors actually have based their new vendor proprietary controllers on the OpenSDN standard. This is also called Open Daylight Controller, or ODC. As far as the CCNA exam is concerned, there are 2 other SDN controllers that are both Cisco proprietary. There is the old and now deprecated, but still talked about controller, APIC EM, which only assumed control of the management plane. This was a single pane of glass management implementation, and because it passed instructions to Cisco devices using standards that were already supported, APIC EM was completely backwards and forward compatible. This made it nice because you didn't have to worry about whether a device had an ASIC or whether it didn't, because it just worked no matter what. Each individual device still used its own computing hardware in order to perform the specific tasks necessary. Unfortunately, as this is deprecated, it's no longer an option for your organization to implement, and it is going to become a security risk later down the line as new vulnerabilities become discovered, which are no longer being patched. Instead, today, Cisco usually pushes the Cisco ACI controller, or application-centric infrastructure. The ACI controller is a true SDN controller to the max, where it will actually take control all the way down to the control plane, meaning it's actually passing the forwarding tables necessary for each device to do its job. This is very powerful, but it also means that it's a lot more intrusive, and because you're giving up everything all the way down to the control layer, this is why ACI requires that each individual device has an ASIC installed, because that ASIC is basically the only thing doing its job after a device is integrated into the SDN. Now, naturally, there are more controllers than just this. I've already mentioned several controllers already. There's the TP-Link Omada controller, there's the Ubiquiti Unify controller, or there's the Palo Alto Panorama controller. There's dozens and dozens of them. I won't go into all of them, but they do exist and they do perform differing levels of control over each individual device, though most draw the line at the management layer. Software-defined controllers usually communicate and accept instructions using an application programmable interface, or API. An API is simply just a piece of code that provides information and instructions to a particular device. In order to make sure that these APIs can be easily programmed and you don't just have to learn a whole new way of doing things, usually SDN controllers will accept what's called a restful API. A restful API is quite simply an application information programmable interface a collection of code that's been organized to conform to several requirements when it comes to APIs. We usually refer to these as RESTful APIs. If they meet the RESTful requirements, they are considered a RESTful API. Naturally, the first requirement of a RESTful API is that it uses a uniform interface. This means that whether you're trying to provide instructions to a Cisco switch or a Juniper switch, they're both going to utilize a uniform interface, and it doesn't matter whether you're writing this interface using Python code or organizing it using something else like JavaScript object notation, JSON. It's going to work either way because your information has been organized in a uniform manner that is used by all devices in your SDN architecture. Another requirement is that this is a client-server architecture, meaning that certain devices are going to be configured as clients and certain are going to be configured as servers, where the clients are pulling information from the server and the server is providing information to the client. A RESTful API is stateless in nature, meaning that all of the instructions and information for the request are contained in each individual request. This means larger requests, but it also means that your devices don't have to keep track of the requests that have already been made to it. This stateless operation makes it easier for storage capabilities of each individual device, meaning more cost cutting on the manufacturer's side and a little bit more work on your part, but it also means that each individual device gets a full set of instructions every single time. RESTful APIs also include a cacheability statement, whether a device should cache certain pieces of information or whether they should not. This is different from the stateless requirement that I just mentioned. This is for caching information that can be used later on, such as if we're providing forwarding tables to each individual device, you wouldn't want the device to implement a forwarding table and then immediately just throw it away. You want to keep that in storage so that the ASIC can continue forwarding using that cached information. These need to be implemented through a layered architecture, meaning that each individual device should be able to communicate whether it is a direct connection between client and server or whether there's an intermediate device in the middle. Some SDN architectures can include intermediate controllers that will pass information from the primary into the client devices. This layered architecture has to be supported by RESTful APIs. And finally, they are code on demand, which this is an optional statement because maybe you might not want to be providing static information to each individual device. Maybe sometimes you might be providing a piece of code that you actually want that device to implement. You can do this using APIs, but you also need to include that code on demand statement that allows the device to know, oh, this isn't information, this is actually a piece of code that I need to be running. It's an applet, it's something that needs to be done on my particular device in order to perform a task I'm supposed to be doing. These are the requirements for a RESTful API. So just to reiterate, a uniform interface, a client-server architecture, a stateless operation, cacheability statements, they need to operate in a layered architecture, and they are code on demand. Normally, SDN controllers utilize what are called northbound APIs and southbound APIs, or just northbound interface, southbound interface. A northbound interface is the connection between the controller and whatever application is sending information to it. These northbound interfaces are normally a RESTful API that has been written by a human. They're formatted in a lot of commonly used markup languages or data serialization languages. These are being formatted in methods that a lot of individuals would have a lot of experience in, such as Python, JSON, YAML, or XML. Southbound interfaces, on the other hand, are the connections between the SDN controller and the individual devices within your SDN fabric. There are two main ones that Cisco discusses in their Cisco CCNA certification. One of these SBIs, southbound interface, is the openflow SBI. Openflow is an open standard that was designed to be used with the Open Daylight controller. Since ACI is very loosely based upon Open Daylight, it can function utilizing openflow. However, it doesn't work the greatest. I know a few organizations that are attempting to implement software-defined networking that utilize a Cisco ACI controller and an openflow SBI because it is open source and lower cost. They're not very happy with the implementation. There are bugs that need worked out, and it is getting better over time, but much more likely Cisco's going to try and sell you their own Cisco proprietary SBI, which is called opflex. Opflex was designed to operate completely in tandem with the Cisco ACI architecture. So just to reiterate, you as a human are going to be providing instructions to the SDN controller using a RESTful API, and then the controller is going to pass information to the end devices using either an openflow SBI or an opflex based API. This is where a lot of discussion about software-defined networking ends, but I did want to bring up another Cisco practice which is starting to gain a little bit of traction, and that is called SD access. SD access, SDA, software-defined access, whatever you want to call it, is an implementation of software-defined networking that is specifically designed for LANs. Now, one of the biggest things about software-defined networking, it doesn't lend itself to LANs very well. Software-defined networking is normally only being implemented in data centers simply because of the sheer amount of cost and the sheer amount of problems when it comes to trying to implement at a LAN level. Or one of the biggest reasons for this is that SDN architecture usually recommends utilizing a spine and leaf topology. A spine and leaf topology is a form of partial mesh where you have two layers of devices, and each device at each layer connects to every other device within another layer, but not within its own layer. This means that instead of a 3-layer architecture like you're supposed to build with a LAN, your data centers are only going to use a 2-layer architecture. This eliminates the need for things such as spanning tree protocol because there are no switch loops being created anymore, but it also means that there are redundancy problems if you try and implement this in a LAN environment where you're supposed to deploy your core and distribution layers in pairs. That's why SD access was created. It's a way of implementing software-defined networking, but in a LAN architecture rather than a data center architecture. SD access still utilizes things like the ACI controller in order to do its job, but it also allows us to do something really neat. One of the biggest problems that we have when it comes to networking is mobile users. If we have users that travel a lot, and one week they might be working in the Seattle office, the next week they might be working in the Portland, Maine office, the next they might be working in Fort Lauderdale, the next they might be working in Houston. This is going to be a huge problem if you're trying to build a network where that user needs access to very specific networks and very specific data sets. This is where SD access comes into play. SD access creates a software-defined networking fabric, which is built up of an overlay and an underlay. Your underlay is the traditional networks that we spend most of our time in school learning how to build. These are the networks that utilize things like spanning tree protocol, that utilize routing protocols. These are layer 2 VLANs with layer 3 subnets applied over the top of them. But for SD access, we now add what's called an overlay, which is just all of the new crap built on top of your traditional network. What an overlay does is it utilizes what's called a VXLAN, or virtual extensible LAN. VXLANs map a user's login credentials to a specific endpoint in a network. SD access architecture requires a routed access layer. This requires ultra segmentation, where every single connection to every end user is a separate /30 subnet. This would be extremely difficult for a human to provision, which is why this is best left to an SDN controller. When a user logs in, SD access uses a protocol called Llisp, the Location ID Separator Protocol. Llisp creates endpoint IDs, or EIDs, for each individual device, and when a user logs in, it will map that end user to a specific endpoint ID, and then it will create a VXLAN tunnel, which is a point-to-point connection between it and a virtual network segment where everyone else in that particular network needs access to the same resources. In order to pair this user credential with this endpoint ID, that means we also get to implement other Cisco appliances as well, such as the Cisco Identity Services Engine, or ICE. And naturally, we have to have some single pane of glass management to see all of this crap, which means we're also going to be utilizing Cisco DNA Center, which is another extremely expensive appliance. You can see SD access is not cheap, but it does allow us to do a really cool thing. It doesn't matter which desk a employee sits at, it doesn't matter where they're at in the organization. When a user logs in, their user credentials are mapped to an endpoint ID and they get access to the same materials every single time. It's a really neat concept, and it's extremely complicated compared to what a lot of other vendors do, but it's also more in-depth than what a lot of other vendors will provide as well. I know that's a lot to take in, but that is software-defined networking in a nutshell as far as the Cisco CCNA certification is concerned. If you have any comments, please feel free to drop them down below, and I will see you all here next time at Brainmelt University.